Hello, I would like to present the Pigeonhole Principle and its applications. This is the agenda of my speech. First, short introduction, then understanding the Pigeonhole Principle, some basic examples, mathematical applications, computer science applications, real-world applications, interactive quiz, and conclusion. First, introduction. What is the Pigeonhole Principle? It is a fundamental concept in combinatorics, and why is it important? Pigeonhole Principle may solve problems across mathematics, computer science, and everyday life. The goal of this presentation is to understand the principle and explore its diverse applications. Understanding the principle. What is the definition? If you have more items than containers, at least one container must hold more than one item. Metaphor: placing pigeons into pigeonholes. More pigeons than holes means some holes have multiple pigeons. And there is a mathematical formulation of this. If n items are placed into m containers and n is bigger than m, then at least one container contains at least sale of one n divided by m items. Basic example. Socks in a drawer and scenario. A drawer may contain 10 black and 10 white socks mixed together. There is a question: how many socks must you pull out blindly to guarantee a matching pair? The answer is 3 socks. Explanation: there are 2 colors, black and white, which is equals to 2 categories. By selecting 3 socks, the Pigeonhole Principle ensures at least 2 socks will be the same color. Another example is birthday paradox simplified. This solution may be totally different than the one which intuitively come to us. The statement is, for example, in a group of 23 people, there is over a 50% chance that 2 share the same birthday. Why? Explanation is that 365 possible birthdays, and there are 23 people, which create 253 pairs, which is described by this pattern here. And pigeonhole application: more pairs increase the probability of shared birthday. So this is different than what our intuition may help us, tell us. But for example, if there are 50 people, the possibility is even bigger. Mathematical applications: integer sequences. The problem: any sequence of 10 integers between 1 and 9 must have at least 2 equal numbers. And explanation: possible integers 9 options, items chosen 10 numbers, and since 10 is bigger than 9, repetition is guaranteed. So it may work a bit different than our logical point of view, and what would be our answer without all these patterns, but later we will observe how it may be used. Handshake problems. Scenario: at a party with 10 people, each person may shake hands with any number of others. Question: prove that at least 2 people shook hands the same number of times. And the solution: possible handshake counts per person 0 to 9. Impossible for one person to have 0 handshakes while another has 9, since that person would have had to shake hands with everyone. So only 9 possible handshake counts for 10 people. By the Pigeonhole Principle, at least 2 people share the same handshake count. Let's go into computer science applications example. And here we can see hash functions and collisions. Hash functions map large datasets to fixed size hash values, and Pigeonhole Principle, more possible inputs than hash outputs leads to inevitable collisions. Implication, importance of collision resolution strategies in data structures like hash tables. Data compression, the concept is to reduce the size of data files, and there are of course limitations. Not all files can be uniquely compressed into smaller files without any loss. The reason is limited numbers of smaller file representations, and Pigeonhole Principle here guarantees that some files must share compressed forms, leading to potential data loss. Real-world applications, for example, haircut example, and the statement, in a city with over 1 million people, at least 2 have the same number of hairs on their heads. How it works? Explanation. Average human head has less than 150,000 hairs. Pigeons, 1 million people. Pigeonholes, 150,001 possible hair counts. And since 1 million is bigger than 150,001, duplication is certain. And room assignment scenario, assigning 13 students to 12 dorm rooms. Conclusion, at least one room must house at least 2 students. And time for interactive quiz. You may stop the video and try to solve this by yourself. The question is, in a school with 27 students, prove that at least 2 students have names starting with the same letter. And there is a hint. Letters in English alphabet 26. And the students 27. You can try to solve this, and let's go into the answer. Answer. By the Pigeonhole Principle, with 27 students, items, and 26 letters, containers, at least 2 students share the same initial letter. Extended Principle. Generalized Pigeonhole Principle. The statement is, if n items are placed into m containers, then at least one container holds at least sale of n divided by m items. An example, distributing 100 apples among 9 baskets, minimum in 1 basket, is sale of 100 divided by 9, which is 12 apples. Usefulness determines minimum quantities in allocation problems. And the next topic is applications in scheduling scenario, scheduling 25 classes over 5 weekdays. The question, what's the minimum number of classes that must occur on the same day? And here's the solution. Sale of 25 classes divided into 5 days, which is equal to 5 classes per day. Conclusion, at least one day will have at least 5 classes.